about accelerating engineering innovation with Wolfram. Francis and Archie are the co-founders of Carnot, and we'll be taking a deep dive and exploring how Mathematica was used to accelerate innovation and how it played a huge role in the technical development at one of the UK's top mechanical engineering startups. So please welcome them today.
Thank you very much, everyone. As you mentioned, I'm Francis. I'm one of the co-founders of Carnot, and I'm joined by my co-founder and CEO, Archie. And we're well aware we've inherited the post-launch graveyard shift. So at the very least, we're going to try and use pretty slides and catchy slogans to get everyone excited. And so that's exactly what we're here to talk to everyone about. It's how we've used Mathematica to not only enable our innovation, but actually accelerate our development pathways as well. And for those that don't know us, we are a UK-based tech company currently tackling one of the most difficult challenges of net zero right now, which is trying to decarbonize the hardest sectors like heavy-duty machinery, marine, and prime power. Currently responsible for about 13% of global CO2, and most worryingly, with no actually production-ready solutions to achieve net zero. And we aim to do this by developing the world's most efficient net zero fuel agnostic powertrain, which I know is a mouthful. So let me try and explain that. And really the core technology uses advanced technical ceramics and super alloys to make cooling systems and engines, which are the biggest drivers of inefficiency and emissions in modern engines. But we took it a step further and actually designed the entire engine architecture to be completely fuel agnostic, running on everything from hydrogen, biofuels, e-fuels, ammonia, to accommodate all the variation of new infrastructure that's going to be part of a net zero world. And so this requires not only serious innovation, but the right kind of tools to actually execute this. And so in the context of startup, well, picking the right tools, we often have very different drivers to standard industry. We have much tighter budgets, smaller teams, but most importantly, pressures from investors to keep things to very tight timelines as well. And it means that working with standard industry tools don't necessarily work, because often these black box toolkits, not only do they are very expensive, they require training and a large amount of computational power, but as the name serves, they are black boxes. They don't offer agility and flexibility when using them to actually foster true innovation and allow us to build sort of core competency in the way that we design our technology. And it often leads to, these black boxes leads to this kind of void between generating results and actually understanding what it is you're actually creating here. And also these tools, they're often made for industry, for the standard status quo. And so they don't really work when you throw a massive step change in ideas at them. They often fail. And so they can't really be expected to foster true innovation, true step changes in ideas. And so often, like us, you have to revert to a very first principles engineering approach that allows you to really tap into what you're trying to develop. And we've used Mathematica as a key tool to be able to do this. And so just by way of example, this is a traditional verification validation curve which dominates most engineering processes, right? But the problem is it's a very, very slow process, and especially for hardware, it's incredibly expensive to iterate through these cycles, which is something that we really can't afford to do. So what we do is seek out tools and processes that help us optimize and streamline this process. And in particular, we use things like multi-fidelity simulations, going all the way from 0 to 3D at a component system level, with Mathematica being especially useful and important in the 0 to 2D region to help accelerate this. And what that allows us to do is actually start validating our engineering at different dimensional levels before we get to physical prototyping. So validating our Mathematica simulations against 3D simulations with other toolkits. And so ultimately what we can end up with, and what Mathematica has allowed us to do, is to create a much more integrated approach with a series of more iterative processes that ultimately allow us to build much greater confidence in our design and engineering before we get to very capital intensive prototyping phases. And Mathematica, as I keep saying, has been an incredible tool for being able to do this. So I'm going to hand you over to Archie, our CEO, to talk a bit more about how we've actually used Mathematica.
Thanks, Francis. So just to give you a bit of background, we're currently testing our proof of concept prototype at our test facility in London. And by next year, we want to refine that into a bench prototype which achieves 55% brake thermal efficiency, which we believe will make it the most efficient engine ever run. So today I'm going to be presenting the 1D simulation that we created in Mathematica to predict the performance of that bench prototype. And I'll finish by showing how our 1D simulation for the proof of concept prototype ties up with the results we're getting now. So that's a bit of background. Just on the engine configuration. So it's a 50 kilowatt prototype with a single cylinder run at 4,500 RPM and a swept volume of 250 cc. So very high power density. So just in terms of the overall philosophy, we have three core pillars to it: the 1D simulation, which we created in Mathematica, 3D combustion simulations, which we run in ANSYS Forte, and then 3D gas flow simulations, which we run in ANSYS Fluent. And there's various iterations that we do between these. So the 1D simulation provides the trapped air, charge air, mass, temperature and composition to the 3D combustion simulation, which then starts and feeds the heat release rate back into the 1D simulation. You've also got a loop between the 3D gas exchange simulation on the bottom right there and the combustion. So the gas simulation will tell you what swirl you have at the point you start combusting, and then you can run your 3D gas simulation. And then on the left there, you have the 1D simulation also interacting with the gas exchange simulation, telling it what the temperature and pressure will be at the exhaust port opening point. So this is just a schematic of the 1D simulation which we built. So you've got the in-cylinder thermodynamic cycle, you've got the gas exchange process, the heat release rate, the heat transfer, and the blow-by leakage. And I'll show you a bit of how we built some of those as we go through. So it's built from it's based on fundamental principles. So it's based on applying the steady state energy equation to a control volume, which in this case is the combustion volume. That's just an example, two-stroke piston there. And the first two terms in the steady state energy equation are the rate of change of internal energy with respect to both temperature and equivalence ratio. So that's effectively your gas properties. Second is your rate of change of mass with respect to equivalence ratio. So for a single zone simulation, that's zero. You've got no transfer of mass. This is the compression and expansion work term done by the gas. And then you also have the heat flows in and out of the control volume. And lastly, you have the stagnation enthalpy flow. So this is the gas flows coming through the ports, the blow-by leakage, and also the diesel when it's injected into the control volume. So just to show you, the gas properties have been extracted from the Wolfram database. And what we did to try and speed up the process was we downloaded all the thermophysical data that we're interested in into a notebook, so it doesn't have to interrogate the Wolfram database online. And then we created functions to interrogate that data and actually to to smooth out places where there are quite abrupt changes. So these are, there's a plot of isobaric specific specific heat, and then thermoconductivity. And just to give you a demonstration of the difference this can make. So here I have at the top R function interrogating the downloaded data, and then the second line is the thermodynamic data function to interrogate the Wolfram database. So if I just run these, and I need to change that to doesn't know. So yeah, the difference in the run times from those two, when you multiply it by the number of times per crank angle degree we simulate over 3 engine cycles, is 56 minutes. So to put that in context, without it, it takes 15 minutes to run the 1D simulation. So with it, you know, you're talking over an hour. So that was yeah, quite a useful thing to be able to do. The heat release rate is based on an empirically derived correlation by Whitehouse and Way for diesel combustion. So it's split into 2 key parts. The fuel preparation rate, which is the physical process of the liquid vaporizing and entraining with the oxygen, and then the chemical reaction rate, which are shown on the left there. So these are the formulae to those two, the 2 parts. P is the fuel preparation rate based on the partial pressure of oxygen, and then you have the reaction rate, which is that integral at the bottom there. And running that through and comparing it with the 3D CFD simulation, apart from that kind of initial high intensity spike you see in the 3D CFD sim, it actually tied up incredibly well. So, you know, again, validation that the fundamental physics really does work in the 1D simulation. So the gas exchange process, this is just an animation from our 2D axisymmetric CFD model. So you've got the intake chamber on the right there, and you've got the combustion volume at the bottom. You've got the exhaust chamber at the top there. So the exhaust port opens first. The high pressure combustion products flow into the exhaust chamber. Both of those are orange. And then you have the intake port opening once the pressure in the combustion chamber is low enough. And you want all the charge air to displace the combustion product. So as you can see, it's ending up quite a nice blue color, which shows it's got good efficiency. So this is just a schematic representation of the gas flow through the port. So they're piston controlled ports. So the piston there is moving from right to left, uncovering the port in the cylinder, and you get gas flow from the higher total pressure P0 in and T0 in to the lower P0 out, T0 out. So the first thing we did to model this in Mathematica, created an algorithm. We divided that axial length into 20 elements. And we want to calculate the mass flow rate, the pressure drop, and the Mach number of the flow at each of those elements. So the first thing we need to do is, this is ultimately the equation we need to solve, the compressible gas flow, but it has 2 unknowns in it, the Mach number, capital M, and the mass flow rate. So we need to use a numerical iterative method to be able to solve it. So initially we guess the mass flow rate, then we use find root to solve that, solve for the Mach number. Then we calculate the static temperature pressure using those formulae there, which gives us the static density. And the static density can enables us to calculate both the velocity from continuity of mass, but also the Reynolds number, which we then use to calculate the Darcy friction factor. And that all feeds into the pressure drop across each element. So that top expression there. And from that, we have the total pressure at the exit of that element. So we repeat that using a nest function 20 times for the 20 elements. And then we compare that final element exit pressure to our target exit pressure in reality. So then we have a second algorithm which uses fixed point to converge on, repeats that whole process and converges on the correct exit pressure for the final element. So this is the first part of that. It's not there anymore. So yeah, this is just that final algorithm running there, and you can see it basically tends to a value and until it the error reaches a certain threshold, and we have our mass, our sort of accurate mass flow estimate from that. So again, comparing that to the 3D CFD gas exchange model, you can see it ties up pretty well, especially with the intake port. So again, giving us good confidence that this 1D simulation is performing well. The last thing I wanted to show was the heat transfer. So we built a 2D axisymmetric thermal FE model in Mathematica to represent this. I'm showing a couple of components there, not the full thing, so we don't give away our secret sauce, but the first step is to extract the geometry, a 2D section of the geometry as an IGES file from Parametric. We import those coordinates into Excel, which allows us to generate the connectivity code, which we're then going to use in Mathematica. Save the coordinates as a CSV file and import those into Mathematica using the import function. Create a boundary mesh using 2 boundary mesh inbuilt function, then mesh that using the 2-element mesh. And then apply material thermal conductivities using the element marker option. So one of those is aluminium and the other is steel. I've just given a little contoured plot of that. And then we apply the convection boundary conditions using the Neumann value and element marker again. And then we create our 2D axisymmetric partial differential equation and solve that using the ND solve value function. So there you can see the in-cylinder heat transfer that it's predicting, as well as all the heat transfer that's being lost to the ambient and the ambient environment. And we can see that those tie up very well. So it's not breaking the laws of physics. And these are the key results from the 1D simulation. So swept volume 250 cc, brake power was about 40 kilowatts, very high specific power, brake thermal efficiency 58%. And lastly, this is taking a step back and looking at our proof of concept prototype in the 1D sim we built in Mathematica for that. This is how they tied up. So in terms of the pressure traces, so we were pretty happy with that. And again, it's given us real confidence from real test data that the 1D sim is doing what we think it is, and our forward projections are, we've got good confidence that they're also accurate. So thank you very